Okay, good afternoon. Uh, today is our second class, and as I mentioned yesterday, we're going to continue where I was left yesterday's presentation. So today we're going to start the fluid properties, and we're going to mainly talk about various fluid properties and how it is related to the fluid behavior. So at the outset, as you know, like we have already talked about what are the various properties of a fluid, like starting from pressure, temperature, volume, and mass that we talked yesterday. And there are other less familiar properties like viscosities, thermal conductivity, elasticity, thermal expansion coefficient, etc. Also, we talked about what are the intensive and extensive properties, and we started talking about how to know like property is a intensive and extensive properties. That was in yesterday's presentation. So if it is an intensive property, it should be independent of mass of a system, whereas extensive properties are actually depend on the size and the size of the system. So let's move to the next slide. And I think we already talked about this yesterday also. So just to refresh your memory, I just put these slides. I think you can go back to the slides I presented yesterday and understand like how to know a certain properties is an extensive property or it's an intensive property. So let's move to the slides very quickly. I think just to refresh this memory, we already talked about this. What are the densities? How to calculate mass densities? What is specific weight? I think you already talked about all these things yesterday. And how to calculate specific weight. Then specific volume, how to calculate specific volume and the specific gravity. So this was actually up to these slides, slide number 9, I presented it yesterday. I just want to put this slide so that you can quickly refresh your memories and then we start the next slide. So, all right, we'll start from this slides onwards again. There was some interaction anyway. So slide number 12, we are here actually going to talk about viscosity. So what is actually viscosity? As I said yesterday, it's a property of a fluid which actually determine how the fluid is going to resist the movement of the fluid in a particular boundary, within a boundary. Like if your fluid is flowing through a tube or through a plate, the viscosity is going to determine the velocity profile of the fluid. So if you look into this schematic diagram, what actually is trying to say, this is if you look into the x-axis, actually it's a velocity profile. I mean the velocity, whereas the y-axis is the distance, and that curve, the nonlinear, the curve actually it's saying the velocity profile. So what happens when there are two layers of fluid which is moving one past another? There was some sort of resistance which develops between these two layers of fluid, which actually try to resist the movement of one layer of fluid over another. So here in this schematic diagram, if you look at this at a certain distance dy, that on dy, the velocity of one fluid is u, and another fluid is u plus du. So that the relative velocity will be the difference between the velocity of of these two fluids, which is nothing but du, and which is being applicable of a small distance dy. So this du by dy is actually called velocity gradient. So if I go by Newton's law of velocity, what he said that the top layer causes a shear stress on the adjacent lower layer. Similarly, the lower layer causes shear stress on the adjacent top layer. So this shear stress is proportional to the rate of change of velocity, which is nothing but velocity gradient given by du by dy. So the shear stress which develops between these two layers of fluid, when this fluid actually moving past one another, I'm going back to the slide I'm showing here. One fluid is moving at a velocity u, another fluid is moving at a velocity u plus du. So the difference between these two layers of fluid, the velocity difference is actually nothing but du, which is applicable on a small distance dy. So the velocity gradient or the rate of change of velocity is given by du by dy, which is nothing, which is proportional to the shear stress which develops between these two layers of fluid, and the proportionality constant is called du by dy equal to mu dy. The mu is proportionality constant is known as viscosity, or sometimes it's called dynamic viscosity. So this mu is, this pronunciation is mu, is the constant which is called the viscosity. And so what is the equation for viscosity? It is nothing but shear stress by velocity gradient, which is sometimes also called shear strain. As you can see, the velocity gradient is also called shear strains, and the unit of shear strain is inverse of time. So it can be inverse of minute, inverse of second, inverse of hour, but generally SI unit is inverse of second. So let's move to the next slide. Here actually I have derived the the equation, the SI unit for viscosity. As you see, the viscosity is nothing but shear stress divided by du by dy, that is change in velocity over change in distance. So shear stress is what? The shear stress is force by area on the area. So, and the change of velocity, the unit is length over time, and distance is 1 by length. So all these things, and the area is also length square. So if the here length get cancelled, so actually it becomes force into time divided by length square. So force is nothing but the SI unit of force is Newton, time is second, and length is meter square. So the SI unit of viscosity is Newton second per meter square, which is also same as Pascal second. And if I convert it into poise, that is called 10 poise. So 1 Newton second per meter square is nothing but 1 Pascal second, which is equal to 10 poise. Let's move to the next slides. This is where actually I'm talking about the kinematic viscosity. It is nothing but the ratio between dynamic viscosity over density, right? So dynamic viscosity, as you can see, it is given by the symbol mu, Greek symbol mu. It is viscosity by density, or it's called mu by rho. And this SI unit of kinematic viscosity is meter square per second, and the CGS unit is centimeter square per second, which is equal to Stokes. It's sometimes also called Stokes. So actually, if you convert into SI unit, what will be that? That 1 centimeter is 100, so it will 10 to the power 4 Stokes. 1 meter square per second is nothing but 10 to the power 4 Stokes. Anyway, we can, all this thing can be derived later. So what is Newton's law of viscosity? It states that the shear stress is proportional to the shear strain. So if I schematically show it, it should be shear stress should be proportional to shear strain. I think I'll come back this slide. Okay, let's talk about okay, next slide. So if the shear strain is proportional to shear strain, the fluid exhibits or the fluid behavior is known as Newtonian fluid. If there is a deviation in the fluid characteristic, if the velocity, sorry, the shear stress is not proportional to shear strain, then it's called non-Newtonian fluid. So let's talk about what are the different parameters on which viscosity is dependent. So actually the most important parameter is temperature. Temperature highly affects the viscosity of any fluid. Generally for liquid, viscosity of liquid, if you heat water, oil, anything, if you heat it, then the viscosity gradually decreases as the temperature increases. Whereas for gaseous species or gases, the opposite happens. The viscosity increases with increase in the temperature. This is due to the reason that the viscous force in a fluid are due to the existence of cohesive force, whereas for gaseous species, it is mainly the molecular momentum transfer. In liquid, the cohesive force predominates the molecular momentum transfer because the liquid molecules are closely packed. Okay, so what happens when you increase the temperature? The cohesive force decreases, and that's how it actually invariably the viscosity also gets affected and viscosity decreases. Whereas in gases, the cohesive force are small, but the molecular momentum transfer actually is this term predominates. So what happens with the increase in temperature? The molecular momentum transfer of the gaseous species actually takes the shape of the container. Actually, the molecular momentum transfer increases, and therefore viscosity increases. So if I put together these equations or the relationship between the viscosity with this parameter, you can see for liquid it is nothing but mu equal to mu0 1 plus alpha t plus beta t square to the power inverse of 1 plus alpha t plus beta t square, where mu is the viscosity of liquid at a certain temperature, mu naught is the viscosity of liquid at 0 degrees C, and alpha beta are constant for the liquid. So for water, mu naught is given, alpha and beta are given. So you can easily calculate what will be the viscosity at a certain temperature if you know this parameter. For liquid also, the relationship is the same relationship exists. Mu equal to mu naught 1 plus alpha t plus beta t square, and the parameters are given. So anyway, you can always use these equations and calculate what will be the viscosity at a certain temperature. Let's move to the types of fluid. Ideal fluid, a fluid which is incompressible and having no viscosity, is known as ideal fluid. So before I talk about all these different fluid behavior, let's see the schematic diagram. Here, figure 1.2 is showing the shear stress versus velocity gradient. What you can see here, the x-axis is shear strain or velocity gradient, y-axis is shear stress. So if it is a Newtonian fluid, as I said, the shear stress will be proportional to the shear strain or velocity gradient. So it is the linear curve, okay, that is actually exhibits the Newtonian fluid. If there is deviation, you can see this is non-Newtonian fluid. When there is a deviation, that actually called non-Newtonian fluid. There are other fluids also, it's called ideal plastic fluid, which has some sort of residual stress, right? So this much residual stress need to be applied before the fluid starts moving. So that's why it is called ideal plastic fluid. And there is ideal fluid and ideal solid, which actually it's the ideal term which does not exist in real life. So let's now go back to the previous slides and see what are the definitions are. The ideal fluid, a fluid which is incompressible. Incompressible, what is the meaning of incompressible fluid? There is no change in density with increase in what? I talked about it, with there is no change in density with increase in temperature. Okay, so that is called incompressible fluid. Ideal fluid which is incompressible and is having no viscosity, that is called an ideal fluid. A real fluid which is possesses viscosity. Most of the fluid in real life are actually real fluid, that's why it's called real fluid. Newtonian fluid, as I just said, a real fluid where the shear stress is directly proportional to the shear strain, and a non-Newtonian fluid which is a real fluid in which shear strain is not proportional to the rate of shear strain. So that is actually called non-Newtonian fluid. So that's an ideal plastic fluid, a fluid in which shear stress is more than the yield value and shear stress is proportional to the rate of shear strain. So this is more than the yield value, means the yield for the Newtonian fluid and non-Newtonian fluid, the yield value is 0. But for the ideal plastic fluid, this much yield value has to be there. Then only the fluid will start moving. So this much residual stress, residual shear stress has to be applied before the fluid start moving. I think you can all get all these equations from M.N. Rahman's book. I think all nicely been explained. Even some basics book which I mentioned during the onset of the semester, I think you can get all the equations. Let's move to the next slides. This is I have taken from M.N. Rahman actually to show you what are the different fluid behavior. So here one is actually Newtonian fluid, 2, 3, 4, 5 all are actually non-Newtonian fluid, which exhibits that here actually one is Newtonian, so shear stress is proportional to shear strain, but for other fluid the shear stress is not proportional to shear strain, and actually the fluid either the viscosity increases or decreases. So if viscosity decreases with increasing shear strain rate or shear strain, that is called the shear thinning or pseudoplastic. Whereas if the viscosity increases with increasing shear strain or strain rate, that is called shear thickening or dilatant fluid. So I'll come to the next slide. So Newtonian fluid cannot be considered a constant independent of du dy. Newtonian, but other fluid, non-Newtonian fluid actually, this is where actually is very important. Non-Newtonian fluid depends on the strain rate or the shear strain. Okay, so non-Newtonian fluid, as you change the shear strain or strain rate, the viscosity is going to change. Whereas Newtonian fluid, the viscosity is independent of shear strain. So let's move to the next slides. I think there is some disturbances or what? What happened? Okay, I think it's came. So this is pseudoplastic fluid. The viscosity decreases with increasing velocity gradient or shear strain, as I mentioned, and dilatant fluid viscosity increases with increasing velocity gradient. I think I already mentioned this. So let's go to the something. Okay, so we're going to solve some numerical. This is very important because I just talked now about different aspects of viscosity. How to now you should know how to calculate viscosity for real life application. So here actually a velocity distribution over a plate is given by this equation u 2 by 3 y minus y square, in which u is the velocity in meter per second at a distance y meter of the plate. Determine the shear stress at y equal to 0 and y equal to 0.15 meter. Take the dynamic viscosity as 8.6. Okay, so here we start it again from here. So as I just said that the properties of the for this particular numerical, the parameters are given. So how to solve it? So the equation is given for the velocity is 2 by 3 y minus y square. So you take the first derivative, you get this. Now it is given how to you have to determine the the viscosity at distance y equal to 0 and y equal to 0.15 meter. So you calculate du dy at y0 is just put the value of y0 0.667. Similarly for y 0.15 you calculate the value 0.367. The viscosity is given 8.63 poise. So that is in SI unit it will be as I said 1 Newton second per meter square equal to 10 poise. So just divide by 10 you get 0.860 Newton second per meter square. Now I think you all know the equation tau equal to mu dy dy. You put the value at y0, tau naught will be mu dy dy0. So if mu is given, du dy naught also you calculated. So the viscosity will be 0.5756. Similarly at y equal to 0.15, viscosity will be 0.3167. That's how we have to calculate. So next, let's move to the next slide. This is another numerical given here. Calculate the dynamic viscosity of an oil which is used for lubrication between a square plate. So this is the square plate. Okay, the black one is the square plate of size 0.8 meter into 0.8 meter. So it is actually showing side view. So the square plate has 0.8 meter length and 0.8 meter breadth. And an inclined plane with the angle of inclination 30 degrees. Here the angle of inclination is 30 degrees as shown here. The weight of the square plate is 300 Newton, which is acting downwards. And it slides down the inclined plane with a uniform velocity of 0.3 meter per second. So this particular weight, the plate is sliding through this inclined plane at a velocity of 0.3 meter per second. The thickness of oil film. So the oil film here is being used for lubrication so that the plate can easily slide past on this inclined plane. The thickness of the oil film is given 1.5 millimeter. So from these parameters, you have to calculate the viscosity of the oil. Okay. So all the parameters you have to know, you have to calculate the viscosity of the oil. How will you approach this problem? Area of the plate, you know, like it's already given 0.8 by 0.8, so 0.64 meter square. Angle of the plane given 30 degree. Weight is given 300 Newton. Velocity is given 0.3 meter per second. The thickness of oil film also given. That is nothing but du by dy. As and if you remember the dy, the thickness of the oil film is actually because over that distance only the plate moves or slide past. So the thickness of oil film will be 1.5 millimeter. And let us assume the viscosity between this plate and inclined plane is mu. Now the weight component along this plane will be either W sin 30 or W cos 60, whatever. You can calculate that will be 150 Newton because it is making an angle of 30 degrees. So it will be W sin 30 or cos 60. That is okay. You calculate 150 Newton. That is the amount of weight, the force acting in this direction. Okay, because the weight is in this direction, but the weight component acting in this direction, along the direction where the plate is moving is 150 Newton. The shear stress, then what will be the shear stress? The shear stress is force divided by area, 150 divided by 0.64, that will be the shear stress. Now you know this equation, du, how to change in velocity, because the stationary state, the velocity is 0. So the du will be u minus 0, that will be 0.3 meter per second. That was the original u. And dy I already mentioned, 1.5 into 10 to the minus 3. You put this value and you calculate the viscosity of the oil as 11.7 pounds. So that is the problem given. Another problem I have given here, because see, generally I used to solve all this problem in class, because right now that I cannot do here, right? So I have to solve it and show it to you so that you can understand. And then after I'm done with a couple of numerical. I'll give you some home assignment where you can solve this numerical and understand like how to calculate various parameters related to viscosity. So let us look at this numerical first. The space between two square flat parallel plate is filled with oil. Each side of the plate is 60 centimeter. The thickness of the oil film is given 12.5 millimeter. The upper plate, which moves at 2.5 meter per second, requires a force of 98.1 Newton to maintain the speed. Okay. To determine the dynamic viscosity, straightforward again, and kinematic viscosity of the oil if the specific gravity of the oil is 0.95. So what are the parameters given? Area each side of the square plate is 60 centimeter. So the area will be 60 centimeter, 0.6 meter. So it will be 0.36 meter square. Thickness of the film is given 12.5 millimeter, that is 12.5 10 to the power minus 3 meter. Velocity of the upper plate given moving at 2.5 meter per second. Okay. So so change of velocity, because the stationary state again like the previous problem is 0. So change of velocity 2.5 meter per second. Force required on upper plate is 98.1 newton. So shear stress will be force by area 98.1 divided by 0.36. Mu is the dynamic viscosity. So again use this equation. The tau equal to mu du by dy. Tau is 98.1, 0.36, all this parameter. You plug in this value and then calculate viscosity. Mu is 1.3635 Newton second per meter square. That is 1.3635 Pascal second. Now for the second part, the specific gravity of the oil is given 0.95. You have to calculate the kinematic viscosity, right? So you know, like specific gravity, there is a relationship between the density. If you multiply it with the density of water, you get the density of that particular oil. So the specific gravity is given 0.95. The density will be 950 kg per meter cube. Now mu equal to mu by rho. So you get you already calculated mu and divided by rho. So you get 0.001435. And the unit of I think I mentioned for kinematic viscosity is meter square per second. So it will be meter square per second. The next problem, this is a little critical problem. Here actually what happened, a dynamic viscosity of an oil which is being used for lubrication between a shaft. So this is a shaft which is rotating on its axis, okay, and slip. So the shaft and slip, the slips are here. This is the slips, okay. So between these slips, this shaft rotates. It is given that the dynamic viscosity of oil, the oil is being used here. Here the oil are being used. You can see I'm just putting my car. I'm showing using my cursor here and here. The oil are being used. Oil is being used between the shaft and the slip, which is having a viscosity of 6 points. The shaft is of diameter 0.4 meters given, and rotating RPM is 190 RPM. It's rotated at 190 RPM, rotational speed. Calculate the power loss in the bearing for a slip length of 90 millimeters. So the slip, this is the slip, and this is the shaft. So 90 millimeter is the slip length. So what will be the power loss? The thickness of the oil film is given 1.5 millimeter. So let us look at this problem first. So again, viscosity is given 6 poise. So it will be 0.6 Newton second per meter square. Diameter of the shaft given. Speed of the shaft, that is the rotational speed, given 190 RPM. Slip length is given 90 millimeter here, slip length. And so it will be 90 into 10 to the power minus 3. Thickness of the oil film given 1.5 millimeter. So that will be 1.5 into 10 to the power minus 3. So what is the tangential velocity of the shaft? Because the shaft is rotating on its axis. So the tangential velocity will be pi dn by 60. That is the formula, right? U will be pi dn by 60, where n is the rotational speed, RPM, d is the diameter of the shaft. And if you put this value, then you get the velocity, tangential velocity, 3.98 meters second. So using this relationship, tau equal to mu by dy, you can calculate the viscosity, right? The du is given, change in velocity. Already stationary state velocity was 0, so it will be 3.98 meter per second. We just calculated tangential velocity. Dy, change of distance, because the oil lubrication film was 1.5 millimeters, 1.5 into 10 minus 3. So tau will be mu du by dy. Mu is 6 by 10 into 3.98, 1.5 into 10 minus 3. You get viscosity of the oil is actually 1592 Newton per meter square. Okay, I think it will be Newton second per meter square. Anyway, that maybe a little bit mistake is there. So this is the shear stress. Oh, no, I'm sorry, it is correct because I'm calculating tau. I'm not calculating viscosity. So it is correct. 1592 Newton per meter square. I'm sorry about that. So this is the shear stress on the shaft. So the shear force, what is the shear force? Shear stress into area, right? Now for the shaft, what is the shear force being acted upon? It is acted upon on the circumference, right? So actually, the shear force to the area will be circumferential area, that is 2 pi RL or pi dA. Right? The shear stress, you know, so if you multiply by pi dA, because it is happening throughout the contact area between the slip and the shaft, that is 2 pi RL, where L is the length of the slip. That was given 90 millimeters. So diameter of the shaft is, as you all know, like how much is given, 90, diameter of the shaft 0.4 meters. So the shear stress is 1592 into pi 3.1 pi, then d is 0.4 and the length is 90 millimeters. So if you put this value, then you get the shear force 180.05 Newton. And torque will be, what will be the torque? Torque is nothing but force into the diameter by 2 or the radius actually. So you calculate, so it will be the total torque on that shaft will be 180.05 into R, or 0.4 by 2, 36.01 Newton meter. So you can calculate the equation. I'm sorry. You can calculate this power lost, which is actually nothing but 2 pi nt by 60. 2 pi nt by 60 is the formula. So here actually you just put the value of all the parameters. I think I have calculated. Torque I have calculated. You know, then n is the that speed of the shaft. You put this value and the power loss will be 760.48 watt. So that is how you calculate the power loss for this problem. Okay, I think that's and then I have given you this homeworks, and I'll share you the slides so you can take it from that PDF file also, and then please solve this numerical and show it to me in the next class. I think you can all, it's very straightforward. You can solve this numerical and share it with me. Everybody must solve this numerical. Okay, that is the homework assignment. So I'll stop here and then let's discuss if you have any question.